Welcome to the Scalar Learning Podcast, your central hub for all things related to education. Join us every episode for the most up-to-date tips and strategies on how to maximize student potential. Sit back, listen, and enjoy.
Scalar Learning. Give me that Scalar Learning. Scalar Learning. Give me that Scalar Learning.
What's up, everybody? Welcome back to another episode of the Scalar Learning Podcast. Today, we are doing another career spotlight. So last time we did a career spotlight, we talked to Howard Marks, the founder of Activision, and it was all about video games and how math is such an integral part and component of effective video game design. So today, we're moving to a different industry. And the industry that we're focusing on today is construction. So I have a very close friend of mine joining me on the show today who owns a construction company, and his name is Tim Bemis. And Tim lives in Michigan, it's where I grew up. That's how we met years ago, almost 16 years ago, back in Michigan. And he is the co-owner of a construction company called Valdivia Construction. And I'll let him talk a little bit more about what exactly they do. And we've talked about this before in private about math and construction, and he uses math all the time. He's got a really good math mind. And so he's going to explain exactly how math relates to having this type of a business. So for those of you guys out there who have a construction company or you have kids that are interested in construction and building and designing, this is a great episode for you guys. So without further ado, Tim, welcome to the show.
Thanks. How's it going?
Pretty good. It is in the morning here in LA. I know you guys are a few hours ahead. So, and you guys have had really hot weather lately, right?
Yeah. It's actually been really nice. Like no rain, maybe a little sprinkle here and there, but in the 80s, sunny.
Very nice.
It's been a lot of fun.
Yeah, I usually avoid Michigan in the winter months for the most part, though I go home every Thanksgiving. And when I do, Tim got married a couple years ago. And at the speech, I gave a speech at his wedding. I was one of his best men. And at the speech, at the wedding, in my speech, I told Laura, his wife, I was like, I know Tim's getting married. I know this is happening, but we still got to have our boys' night every time I come home, just one night. And of course, she agreed. So that's pretty cool of her. All right. Sorry, go ahead.
I would say we're overdue for one soon.
I know. I got to make it back. So tell us a little bit about your background and the degree that you got in college, and what did you study?
Okay. Well, I always have kind of been involved in the construction industry with my father. It's actually my father's company that started it. So just working as a laborer, as a grunt, in summers in college and high school. But I actually went to college and got my degree in mechanical engineering. So massive math background right there. But it just happened to be when I graduated college was kind of the time where everything stopped in Michigan. There was no auto industry to talk about, no job offers available. It was kind of bleak. So I had the opportunity, just with my math background and a little bit of construction knowledge, not much, I got a job opportunity to work as a project engineer for a large construction firm. And my first project was actually working on the casinos in Detroit. So I jumped at the opportunity, and from there kind of just stayed in the field and enjoyed it. I like the idea of not being in the same place all the time. Given you may be in your office a lot, doing a lot of paperwork and what have you, but the job sites always change. Maybe 2 years at most, 3 years if it's a really large project. But you're constantly seeing different cities, different areas. It's brought me to Chicago, to Midwest. Most of the Midwest I've built, not too far. But there are the opportunities for me if I wanted to leave. And then it's kind of cool that after you do build something, you can always drive by it or see it and be like, hey, I had a hand in that. My mind was part of that being designed and being built. So that's kind of cool. And then as I worked, I learned more, gained my knowledge, and then kind of went off on my own, took my father's company and working to make it larger and bigger than it is now.
So before you went back to Valdivia Construction and started running the business alongside your father, for kids who are interested in maybe becoming a project engineer at a corporation, what is that? Can you just describe a little day to day? What was it like? What were the things that you had to do as a project engineer?
The main thing as a project engineer is you're kind of the main gear of the main sprocket of the whole thing. Just making sure everything runs smooth. You gotta review all the drawings. You work from the beginning with the estimating team. Make sure you guys get your price right. Get all your bids in for your subcontractors. Work with them to make sure they know exactly what needs to be built. You work with the architect in the planning phase. Now, given you're not the designer, but you do some design build on site if something needs to be changed. You do have the authority to say, hey, we need to build it this way. So you're in a lot in the planning phases, and you make sure everyone has that information. If a subcontractor, didn't know some wall had to be built in a certain area, that's kind of going to fall back on you because you didn't relay that information to him and kind of teach him what has to be done. And then once you pass the planning phase and you're actually in their building, you're overseeing any changes from the architect, going over changes with them, any problems that may come up. You're going over the billing. You're basically just managing the whole job and making sure you just got to make sure nothing is built wrong. You're overseeing everyone, and you're kind of a leg in each area. You're a little bit of a superintendent. You're a little bit of an estimator. You're a little bit of the whole project manager. You're a little bit of an architect, and sometimes you may have to get your hands dirty and help build something in case something's behind schedule or behind time. Make sure the materials are there. So it's pretty hands-on, pretty involved job.
For kids listening who don't know what a subcontractor is and what bids are, can you just explain very briefly what are subcontractors? How do the bids work?
Okay, when you work on large projects such as I do, you're the main person that an owner would hire, and you're called the contractor. Now, when you're a contractor, usually you don't self-perform all the work. Now, I can self-perform in my company. Mostly I do concrete. I can physically do the concrete. That's self-performing your own work. But I'm not a plumber. I'm not an electrician. I'm not a heating and cooling guy. I can't install a furnace. So what I do then is I go out and hire another company under me, but we're still under the main umbrella of the owner. That goes the owner, then me, then the plumber, and the plumber's my subcontractor. I subcontract him from my main contract to do the work. And then a bid is just basically his price, what he's going to charge me to, run these pipes, install this furnace, etc. And then I take that price and I want that to kind of be the best price I can get because I had already gave the owner my price. So that difference in price is usually my profit of what I can make on the job. And that's how you profit as a contractor. Now, some companies you build for, they may say, hey, we want you to build this, and this is how much we're going to give you. And they don't want any kind of markup from your subcontractor. So basically, they're just paying you to manage them. So whatever their price is, it goes straight to the owner, which is fine because the owner's giving you a fee for a job of just overseeing them.
I see. Okay, thank you. That was excellent. Now, let's just talk really quickly. We're going to jump in very shortly into how math relates to your line of work, how you use it on a daily basis. Can you just quickly tell us what are some of the things that you've built over the years that you think are really cool in Michigan that are your favorite things to point out?
Well, probably the biggest was the first jobs I was on is probably the casinos, MGM Grand Casino, Greektown Casino, and Motor City Casino. Being working on all three of those, that was actually really exciting. Seeing them going up, seeing them finish. I mean, every time I go in there, especially like MGM, because that was the one I was on the most, like I had my wedding party there. You were a part of it. Just that, we stayed in there, and I just know the fact that this hotel, I kind of knew where all the plumbing went, all the pipes went, what exactly was there, what was, that I helped build this place. So that's pretty exciting. As far as excitement, that's probably the coolest I've done in Michigan. Retirement communities, the company I worked for, they specialize in retirement homes. So, when I drive by and see those, it's nice to know that I worked on those. And it was pretty rewarding because we did a lot of volunteer work when we were there too with the seniors. So it was actually a pretty rewarding job when we were working there. But now in the past years since I've been with Valdivia Construction, we actually specialize in industrial work. I don't really do the commercial as much. So I specialize in factories and press plants, and we're really getting to a small area of machine foundations, which not a lot of companies do. So we're actually in high demand for that because we're one of the better companies in building machine press pits or machine foundations, which is pretty intricate work, because if that isn't correct, then this $1 million machine that they bought to build their company around won't work properly.
I see. Okay. Very interesting. Very cool. And yes, I've been to these different casinos many times. I'm not as familiar, of course, with the industrial side, but MGM Casino, all those are awesome, fun to go to. So Tim, now let's talk a little bit about math. How is math? So this is again for kids who love construction, who love to build like you do, and are interested in this career path. What are some of the ways in which you use math on a daily basis on the job?
Okay, I'm going to go. Math is huge in construction, all the way up from, the architect all the way down to the guy with a shovel in his hand. So I'm going to just go over to kind of the points that I know me and my workers use on an everyday basis. And if I didn't know this stuff, or if they didn't know the majority of this stuff, then work's going to be very slow. We're not going to get the job done, and it's going to be wrong, and we're probably going to be out of business. So just to start off the right off the bat, the thing that's used every hour probably of a job, and people don't think twice about it, is a tape measure. And when you're using tape measure, you're dealing with fractions, and that's huge. You got your quarter inch, half inch, eighth, what have you. And with those fractions, you have to be able to add and subtract them quickly. And they're not equal fractions. You're not just adding halves. You're not adding quarters. I may have a dimension. Hey, I have a quarter inch here, and I got to add an eighth. Go get me 3/8. Something. And I'm not going to have a calculator with me to do that. I need to be able to do that inside my head. Now, if I was sitting at a plan table and I'm going over it, doing a lot of accurate drawings, or say estimating a job, then yeah, I may have a calculator just to make sure there's no mistakes and I'm adding tons of numbers together. But when you're in the field, you're not going to have a calculator. Your hands are dirty, so you're not going to want to pull out your, $800 iPhone to touch it, to try to add it. And plus, someone's going to yell at you while you taking your time. What do I need? What do I need? It's pretty fast paced. So it's not practical to have a calculator in the field. And with fractions, you have to be able to convert them to decimals too. You have to be able to convert fractions of inches and also feet into decimals. As an example, most architectural drawings, they'll be in fractions. You'll see 10 feet, 4.5 inches. But in land surveying drawings, which we work with a lot because grade is very important, how deep we're putting something, how high something goes, that's usually all in decimals. So if they give me, this has to be at, say, 50.525. Okay, well, what is that? That's 50 feet, 50 feet, 6 inches and a quarter. So you have to be able to flip-flop between the both of those. And Also, you have to be able to know your fraction. So if I have an eighth and an inch, a lot of times I need to know the decimal of that to add them up. And that would be 0.125. Sorry.
Very good. What is, can I try you for 7/8?
8.75.
Right.
I'm sorry, 0.875.
There we go, 0.875. Excellent. Yes, that's right. It's cool because actually, so I've been teaching a fourth grade math class for the last, 3-4 months now, and that's what we've been covering right now in fourth grade is basically using decimals, using fractions, and how the two relate, how they're the same, converting from fractions to decimals, vice versa. There's a lot of work in fourth grade, and it continues on fifth grade, sixth grade. These are things that really form the foundation of everything you're going to use for algebra, pre-calculus, so on and so forth. Super important. And it's so great to hear that, because I hear these objections all the time. Kids are saying that why do I need to learn this mentally if I can use a calculator? And here's a perfect example when speed is an issue. I beat calculators all the time when I'm multiplying, dividing, whatever, because the fact is that a calculator, in order to compute something, it necessitates the typing in of the numbers. And when speed is really important, if you can just do it in your head, it's much faster. You don't have to type anything. It just happens mentally. So that's awesome. So you talk about fractions and decimals. What other math concepts have you used on the job?
Well, one quick one kind of in that area of converting is just standard of metric. Especially working here in the U.S., a lot of our drawings for a lot of the machines and stuff will come in metric. And not many people can measure in metric. You don't see many metric tape measures out there. So you have to be able to kind of convert back and forth. 1 inch to 2.54 centimeters. So
oh, wow.
That's kind of what you need to be able to flip back and forth. Okay, so beyond conversion, that's probably the number one thing that's used constantly. That area that I discussed. The next areas are very important and they're used regularly, but that right there is, if you don't have that down, you just don't even try to work in this area, basically. So the next kind of big area, which is kind of important from my side, being a boss, because this can make or break you kind of financially, is learning areas of a volume of something, such as concrete, how much I'll need, grading material, such as how much dirt, how much stone I'll need, how much dirt or stone I'm going to be taking out so I can price it correctly, order the right amount of trucks, have the right number of guys there. If I have a hole there and I got to dig this hole, well, I'm just not going to dig it. I got to know where to take it. I got to know how much it's going to cost me. So I got to know how much dirt is there. So that's pretty important to know that to the areas basically. Now, of course, the easiest would be of a rectangle or square. Just an example, if I was pouring concrete of an area and it's 10 by 20, you got 200 square feet. And then you want to find the cubic volume. So how deep are we going to pour that? Let's just say we're doing a 6-inch slab. So we're going to times that by a half a foot. So now we have 100 cubic feet. Now this is where it gets a little more tricky. So 100 cubic feet. Still, how much concrete do I order? Concrete in the U.S. is ordered by yards. So now I need a cubic yard. Well, a yard is 3 feet. So a cube is a cube, all same on every side. So 3 times 3 times 3 is 27. So you got 27 cubic feet in 1 yard. I divide that 100 by 27, and it comes out to roughly 3.7 yards. That number is important because when I order concrete for this job, I need to order. Now, you can't order 0.7 yards. So I'd round up and order 4. Okay. The reason that's important is if I order too much, especially on a big job, when I'm pouring, like say 100 yards, a yard of concrete roughly right now in Michigan is about $130. So every yard I'm off, that's $130 I'm paying. Now, I guess I'd rather be a little high and spend the money, which would hurt my pocket because you don't get that money back. You don't return concrete. That's just, boom, burn this money, throw it away. What if I underorder? That's where the big problem comes in. Because if you're pouring concrete, you can't have a stop. Usually what you're doing, you can't have a stopping point. That's going to weaken your foundation. That's going to weaken what you're doing. And the problem is if you order too little, a lot of times some of those companies can't bring you out more right then, especially on a big pour. If it's at the end of the day, good luck getting another truck out there. So if you under order it, you're going to, one, mess up the job, two, piss off the owner, and three, you're not going to get hired again. So that number, that calculation is very vital to my company running correctly and having a good business plan.
That's so that's so interesting. It involves that involves a few different elements from math. It involves volume calculations. I have a lot of my high school kids who are taking their geometry finals last week and this week, and that's what they focus on in addition to area is volume calculations of whether it's cubic prisms, whether it's cylinders, and I'm sure you guys have to do that occasionally if you drill a circular hole and all these things.
No,
and
we would pour columns.
Oh, columns. Yeah, of course. Okay. And you have that, but then you have another element, which Tim has been talking about, which is basically a little bit of estimation or rounding up and doing it accurately with respect to, maybe going a little over so you make sure you don't have too little, but you don't go burning money. And I mean, all these different elements. And again, I'm going to take it back to mental math because if you're simply relying on a calculator, and correct me, jump in if I'm wrong about this, but I have to believe this is correct. If you're simply relying on a calculator and your number sense is not very good, what's going to happen is if you do miscalculate something by chance on your calculator, let's say you type something in wrong, and you don't have a very good number sense, you're not going to recognize that error when it goes down on paper and when you put in the order.
Exactly. You're going to assume that calculator is correct because it's a calculator, and you're ordering wrong.
Yeah, and that's the other importance of mental math. So you get to that point where you're like, wait, where you can recognize that an answer doesn't make sense, and then you can save yourself a big hardship. And that's really cool. I didn't know that you couldn't have if you have a stopping point. So I think correct me again if I'm wrong, a stopping point meaning you pour half the concrete, stop, and then resume the next day. That creates a structural weakness.
Yeah, it creates a cold joint. So basically, you're putting a pre-existing crack in the pour.
Wow!
Because it's stopping and going. Now maybe it could be all right. I mean, there's certain areas there's things you can do to make that right. Like if you were doing a parking lot, it's not that big of a deal. You make the one side flat, and then you just have to dowel metal anchors to connect to the next piece. But if you're doing, say, a wall or a bearing wall, or just something that needs that strength because there's going to be 100,000-ton machine sitting on top of it, then you can't have those stopping points. It's not engineered to have those stopping points.
So in that case, if you had a stopping point, would you have to literally break the concrete and do it again?
Well, I've had times where we've had to remove stuff because of that. We've had to basically cut back and remove to a point where the engineer who designed it was okay with that being from there. It just opens up a can of worms that you don't want to deal with. The kind of thing with that just is going to give you headaches and you're not going to sleep good at night.
Fair enough. Okay, cool. So we've talked about volume. We talked about air. Oh yeah, go ahead.
Real quick on the volume, though, I had one other thing is not everything you measure in the field's a square or rectangle, like how I just gave that quick measurement.
Okay.
You pour something or you pour a wall, it's not going to always be that'd be awesome if it was and make life a lot easier. But you're going to have circles, you're going to have triangles. You basically take an area and you want to break it up to what you can. Like, okay, this is a square, I can measure this. This is a circle. This is so you're going to need to be able to find areas and volumes of like you said, of circles, of triangles, etc. You need to know those measurements.
It's so cool. There was actually just a problem I was working on with one of my students in geometry, and it was actually calculating the volume as well as the surface area of a make-believe castle where it was comprised. And it's so cool to hear this because it just tells me that that was a great problem with a lot of excellent real-world applications. It was comprised of spheres, or half spheres in this case, pyramids on the top of these different towers, prisms, all that stuff. So it was really, really cool. So great stuff. And then in addition to volume and area, is there anything else that you use even regularly, irregularly?
Well, just an example, last week, I just used this, which this doesn't come up a lot, but it was nice to know that I had this in my back pocket to figure out material, basically. You go buy too much material, you're wasting money, and not every place is like a Home Depot where you can take something back 90 days later. So I had to put basically a pipe, a flexible pipe around a catch basin, a sewer, basically. We're building sewers, and we had to put drain pipe around it. So I need to know how much drain pipe I need to purchase because you buy it by the foot. So what I need to do was figure out the circumference of around each drain. So I took the radius, which was 3 feet because it was 6 feet in diameter, so 3 feet, and then the simple equation of 2 pi times radius 3. So I knew I needed roughly just under 19 feet per each hole.
Very nice. Love to see the application of pi and circumference. Very cool.
And then probably like another big thing, that's used, especially pouring driveways or handicap, or even building a roof or building a building is slope. So you can get roof pitch, the slope of the concrete for the parking lot, because I don't know, everyone probably sees that. If you're out in, say, a Walmart parking lot or wherever, and it rains, what do you see the water do? You see it run a certain way to a drain. It's designed that way. That's poured with a certain slope that is calculated. Because if you just pour it, just throw the concrete down or the asphalt, the rain's going to sit there or go wherever it wants to go. That's not how our world and our infrastructure works, especially when you see roads. Where does the water go? To the sides, so where the drains are. So, you got to use slope equation for that. And you can also use a slope equation and work backwards. So say a city might say you can't have more than a 5% slope. Well, if I know my starting point and I know I can have 5% and I know I want to go a certain distance, I can work backwards and find point B and know that's how far my pour is. So that's kind of a cool little thing to be able to know.
So now we've talked about fractions, decimals, we've talked about areas, volumes. What are if there are any other applications, what are they for math and construction?
Yes. Some more trigonometry, big that we use especially carpenters, is Pythagorean's theorem, a squared plus b squared equals c squared. This is very important to make sure whatever we're building is square to a wall, square to a certain area. Out in the open, you're building a box, you're pouring a floor, because if something's not square, if it's off, it could throw the whole job off, could make measurements down the road be wrong, or it just could make something look like crap, honestly. So, that's huge thing to use all the time to make sure whatever you're building is perfectly square. And then once in a while, I've actually had to figure out off a square the length of a certain side of, say, I couldn't measure. I couldn't get over there to put my tape there. Say it was a deep hole we dug, and I need to make sure it was square or measure the side. I've had to use sine, cosine, and tangent, such as, say, I needed the opposite side of this right angle, which is tangent of the angle equals opposite over adjacent. So say I already know I'm at a 30-degree angle, and I know one side will just stick with 30. You got tangent of 30, and then you times it by the 30, and then I know that one side is roughly 17.32 feet. which can help me because I can't get over there to measure it and I need to know. Or it's you need to know that if you're, say, doing property lines, you're trying to figure out how long is this property line to make sure I'm not building on someone else's land.
That's so cool. So for guys who are out there who haven't taken geometry yet, who haven't taken trigonometry yet, let me just quickly explain. So first we mentioned Pythagorean's theorem. That is one of the most common theorems used in math today, and it has to do with calculating side lengths of a right triangle. So again, obviously it has great relevance here. And when Tim talks about sine, cosine, and tangent, these are functions, really more relationships I would call them, but they're considered functions. And they have to do with relationships between angles of right triangles and side lengths of right triangles. More than just side lengths, it's ratios of side lengths. So when Tim talks about taking tangent of a particular angle, the way you would use that on a calculator is, it's really cool because these functions have been programmed into calculators. So you can basically say, all right, I've got a bottom length here of whatever it is, 30 feet. Okay, so let's say from where I'm standing to the wall is going to be 30 feet. And I know that I need to have a gradient or something, an angle of 30 degrees from where I'm standing going up. So if that's the case, how high do I need to build my wall? You can use a function like tangent, where he said you basically take tangent of 30, and then that's going to equal, like he said before, opposite over adjacent. It means it will equal the ratio of, this is hard to explain without visuals, but I'm doing my best. It's the ratio of the opposite side over the adjacent side. Adjacent just means the side right next to that angle. And so then you can basically, using some ratios and proportions, you can then almost like reverse engineer what the height should be. It's really cool. And I know that sometimes trigonometry can be tricky, but this is such a great way to try and understand it because it's a super real world application, a very useful way to put these formulas into play. This was so cool. So for me, this was awesome. Of course, I know Tim really well. We go way back, and I know he's in this industry. But this is actually, honestly, my first time hearing all these cool applications of math. I knew they had to be everywhere in the construction industry, but hearing it, it's so cool, especially with slope. It's such a heavily tested concept on the IC, on the ACT, on the SAT, and these geometry concepts. So that was amazing. Thank you so much, Tim. And again, your construction company is Valdivia Construction. Can you spell Valdivia?
Valdivia.
All right, awesome. So Valdivia Construction, if you're in Michigan, you need any projects, hit him up. And again, thank you guys so much for joining. I hope this was helpful and informative. New episodes during the summer of 2016 will be dropping every day. So please tune back in for more math or education related topics and information. Again, thanks for joining. For the show notes, you can go to www.scalarlearning.com. And if you have any questions or comments for me, email me at huzaifa@scalarlearning.com. That's all for today. I'll see you guys next time. Take it easy.
Scalar learning. Give me that scalar learning. Scalar learning. Give me that scalar learning.